Okay, shall we begin? So it's my pleasure to introduce our guest Mathai to talk about T-Duality, loop space, and Witten gerbe modules.
Thanks very much. It's a pleasure to be here and to give a talk at this fascinating conference. Thanks to Hisham and his collaborators and his friends who have organized it, and also the beautiful excursion yesterday. And I can't resist but say that, I've known Hisham since his PhD days, and it's great to see that he still has the enthusiasm that he showed even in those days. He organized many seminars and was very energetic, and he still is to this day. And he has a great team here, and I'm really happy to see that he's well settled, and yeah, it's a pleasure to see that. Okay, so I'm talking about T-Duality today, which has little connection with, well, it's not M theory, but there is one part, because I'm sort of studying T-Duality on loop space, the Pontryagin class comes up, and a new version of the Pontryagin class appears. So one motivation, so first of all, let me just say that I will start by reviewing work with Peter Evslin and Gerard Evslin, and then the new stuff is work with Fei Han in Singapore. He, unfortunately, due to some dental surgery, wasn't able to come for the conference. Gives his apologies. So one reason for studying T-Duality in loop space, well, loop space, after all, strings are loops. I mean, I'm talking like a mathematician. And the other thing is that, well, what appears on space-time is a shadow of what appears on loop space. That's the philosophy which we take. And we've been studying T-Duality in loop space in different guises. So I might also talk about another earlier version of this. So this is the outline of my talk. So I first review what happens in the case of circle bundles. And then I repackage this so I'll explain what it is, a graded version, and then the Euler operator appears very naturally. And then a loop space refinement, but this is for small loops. You should think of it as motivated by Witten's Dirac operator on small loops, on loop space. And here, so in Witten's case, he got modular forms. Here we get Jacobi forms because there's a twist. And then examples of Jacobi forms are Witten gerbe modules. I'll explain what those are. And then we get a Horry formula, a graded Horry formula here. And if I have time, I'll talk about an earlier version to T-Duality. And so one improvement here is that we can actually get a graded Horry formula. In the previous case, we sort of cheated and got T-Duality on loop space, but we didn't get a Horry formula, which is explicit isomorphism. So let me just, so not everyone knows at least this approach to T-Duality. Some in the audience know it. So I'm going to give a sort of maybe a caricature of what type 2 string theory is. So you have a background flux, H, which is a 3-form closed with integral periods. But this is not enough. You need, say, a suitable open cover, for instance, a good open cover. And then you have 2 forms on this open cover such that H restricted to this open set, U alpha is dB alpha. And you have 1 form such that B alpha minus B beta is D A alpha beta. So the tree form doesn't capture, torsion information, but the full Deligne class, as mathematicians call it, but in string theory, these are tadpole conditions, I heard. So, and it captures integral information. So, and then there are the Riemann-Roman fields, G, which is an even form in type 2b and odd form in type 2a. They satisfy the equations of motion, and this is d minus h wedge G is equal to 0. And you get twisted cohomology here, but you can refine this to twisted K theory. I don't want to state it here. And then there are these two conditions, the Einstein-Maxwell equation, which is in the vacuum, it's Ricci curvature is equal to a suitable contraction of the three-form flux. So H, right? So, and there's a dilaton and axion. But what I'm talking about is like topological T-duality, where these are ignored, but people have studied them with these equations. Of course, there are very few examples if you have this, and if you ignore them, then you have a lot more. It's a more universal kind of construction. So we'll be concerned with T-duality between type 2a and type 2b for circle bundle compactifications of free circle actions with a H flux. So you have a space-time which is compactified to a circle bundle, and you have a H flux, which is not just the three form, but there's additional data. The transformation laws of the low energy effective fields are known as Boucher rules. And however, in the case where the three form flux is topologically non-trivial, the Boucher rules don't give global information, okay? So that although it was known in special cases before, I mean, we wrote down, this is the first paper in 2003, we wrote down the kind of global Boucher rules for circle bundles with topologically non-trivial flux. So let me just recall that. So Z is space-time, and it's a circle bundle over M. And it's determined by the first-gen class, which we can view as a degree 2 class on M with integral periods, and H flux, which is over here. So the T-dual, so you're just given this data, and you construct the T-dual out of this. It's another circle bundle whose Chern class is the push forward of H under pi. So this means you can informally think of it as integration along the fiber, integration along the circle. So you get a integral 2 class on M, and that by pre-quantization is the first-gen class of another circle bundle. And this is the T-dual circle bundle. And then, such circle bundles have a Giesing sequence, and you can define an H flux on this space-time, T-dual space-time, which has the property that when you integrate along the fiber, you get back the first-gen class of the original circle bundle. So there's a small catch here. So H hat is not fixed by this data because, if you take any two form on M, any three form on M and integrate along the fiber, pull it back to the total space and integrate along the fiber, you get 0. So the way to fix this is to go to the correspondence space, or what's sometimes popularly known as the double, is you go to the correspondence space and you say that the lift of these two three forms are equal in cohomology on the correspondence space or on the double space. Okay, so then this fixes H hat uniquely. So the slogan which we put in that paper was that the background flux gets exchanged with the Chern class. And so what the interesting thing was, there's a change in topology of space-time when either the background flux is topologically non-trivial or the Chern class is topologically non-trivial. So this is the thing which we thought was surprising and interesting. So let me give you some examples. Although these are low-dimensional examples, you can take the product with any manifold, and you get general examples. So you can take length space LP1, which is a 3-sphere divided by the finite group, cyclic group Z mod P, and the sphere is the unit sphere in complex 2 space, and the cyclic group acts as e to the I k over p, and it leaves the first coordinate alone and multiplies the second coordinate by this root of unity, pth root of unity. So it's easy to see that this length space is the total space of a circle bundle over S2, the 2-sphere, with Chern class equal to p times the generator of the, say, the volume form of the 2-sphere. So, and here's a fact that this length space LP1 is never even homeomorphic to LQ1 if p is not equal to q. However, LP1 and the flux is q times the volume form, and LQ1 with flux p times the volume form are T-dual pairs by a prescription. Okay, so the T-duality is the exchange of p and q, and here the topology changes. So here's an example I gave in a popular talk that if you take L11, which is S3, and L01, which is S2, the trivial circle bundle, then you get that these two are T-dual pairs, and it's kind of like the donut universe and the universe are T-dual. And I even scaled it, I see, so that's good. And here's another example, and I'll stop with this for in this case. You can look at the Heisenberg group, which is 111 and x, y, z. It's a central extension. So the projection to x, y is this R2, and the z is the reals with the z variable is the center. And for each p, which is a non-zero integer, the Heisenberg group has lattices as such, x, y, and z over p, and x, y, z are integers. And this is a central extension of z squared by z. So it's easy computation shows that the quotient of the real Heisenberg group by this lattice is a principal circle bundle over the 2 torus with Chern number p times the volume, I mean. So, and another fact is that this so-called nil manifold with p is not homeomorphic to the nil manifold with q when p is not equal to q, but these two are nevertheless T-dual pairs, so they have different topology. Okay, so I haven't yet stated what T-duality actually does. I mean, it gives rise to a map which induces degree shifting isomorphisms between H-twisted cohomology of Z and H-hat twisted cohomology of Z hat, and also of the corresponding twisted K theories. So, and in fact, if the T-duality map is assumed to be in isometry, I'll explain this. The radius R circles circle fibers of Z, and the radius 1 on R circle fibers of Z hat are isomorphic. So this is an important feature of T-duality. So let me recall the transform which actually implements this. So let's choose one forms, A and A hat on the circle bundle Z and Z hat respectively. So that's so these two. So I'm A hat, so the hats are on the T-dual. So the the rules for transforming the Ramon fields, these were stated in my paper with Jara and Peter Boutnick. So it's a kind of twisted Fourier-Mackay transform. So if you take a field which is so an invariant form on Z, you lift it to the correspondence space, multiply by exponential of A wedge A hat, and integrate over the circle. So you get something on the T-dual space. So the thing is, when these are trivial bundles, A and A hat are just d theta and d theta hat, and this exponential is the Chern character, the Poincaré line bundle. So it has some geometric meaning. But when there's a flux, this doesn't have an immediate sort of interpretation as such. So let's just, so I muttered something about Giesing sequence and etc., but you can do it directly. So if you take the curvature of A and the curvature of A hat, then you can write the three-form flux as A wedge the curvature, right? And if you subtract these two, you see that you get a basic form. So it's omega, where omega is a form on the base manifold M. And you just declare H hat to be F wedge A hat minus the same three-form omega. And what you notice by just subtracting these equations, that you get that H minus H hat is exact. And actually, it's interesting to talking about exact, whether you can interpret it as a cocycle in some fancy theory, I don't know. So this, so T star maps DH closed forms to DH hat closed forms. This immediately tells you. And so it induces a map on twisted cohomology. A priori could be the zero map. But so the theorem we showed was if you take a metric on the base manifold, lift it to the total space, and then on the fiber you add the metric A symmetric product A, and for good measure you scale it by R squared, and on the T-dual side you scale it by R to the minus 2, and you take the same metric on M and A hat symmetric product A hat. Then what we show is that the invariant forms on Z, so by the way, integration along the circle shifts the degree. So if you start off with the even form, you get an odd form, you get an even form. So it changes the parity. And in fact, that this map is an isometry when you put such metrics. So it induces an isomorphism on harmonic forms, and therefore on twisted cohomology groups, on twisted harmonic forms. So we get this isomorphism of twisted cohomology, which is degree shifting. So before I go on, let me just mention that, of course, this has been extended by many people to torus compactifications. And there's some bizarre new phenomenon happen. I'm not going to talk about it, but different people have different interpretations. We use non-commutative geometry and non-associated geometry. Chris Hull uses the double spaces, which he invented. No, T-folds, sorry, that he invented. So, but I'm not talking about the higher rank case. I'm only talking about circle bundles. So now I want to repackage this. I'll explain why I want to repackage it. So the Hori maps are, again, isometries as such. But the invariant forms on Z are isomorphic to forms on M, and then forms of type K+1 on M, wedge A. So this is an old theorem which you can prove directly, but it was known to cut on. So the connection provides this isomorphism. So this is a kind of dimension reduction, so to speak. Then T, when you use this dimension reduction, the T dual map, it maps F plus G wedge A. So that's of this form. So if you just do this computation using the Hori formula, you get -1 to the K+1, G plus F wedge A hat. So it's kind of switching the G and F, right, with a sign, overall sign. So this is the dimensionally reduced form of T-duality. And that's for the twist given by H. But supposing I take an integer, M, and define the level M Hori map as such. So it's now twisted by M times H. And this is the transform. And a little calculation shows that D plus MHG is 0. And since you have this relation by just multiplying the original relation by M, it's not hard to see that this level M Hori map is applied to G is an invariant form on the T-dual. So, and D plus M H hat of the level M Hori map. So it satisfies this equation. So let's denote this thing D plus MH closed forms, which are invariant. The level M Hori map will change the parity and take forms on Z to forms on Z hat. So let the formal variable Y encode the level. This is kind of like, for people who know, it's kind of like the chi-Y genus of Herzebruck. So that is define this T-dual map from these forms to the forms on the T-dual. So take a representative omega m, y to the m. So omega m is in here, so it's closed under D plus mh. And it has to be of the form fm plus gma. And applying the level m Hori formula, we see that you get the same switching. So fm plus gma is -1 to k, gm plus fma. And applying the reverse level m Hori map, you get an m over here. So that's the new thing which happens. So m times fm plus gma. So, and if you compose the two, you get m times omega m y to the m. And this is, if you notice, it's just y d dy of this form. And that's the Euler operator. So it agrees when m equals 1 to the usual Hori formula, which says that if you take the Hori formula and in the reverse one, you get -1. Okay, so that's the, so T-duality applied twice gets -1. Here it encodes all the twists. So H and MH for every M. And the reason is, so when I go to loop space, you have to take tensor powers. And the tensor powers of a gerbe module, is a gerbe module for the tensor power gerbe. So you have to take all powers of M and not just a single M. So this is when I talk about the loop space refinement. So motivated by string theory, people have been trying to generalize concepts such as vector bundles, Dirac copies, T-Singer index theorem to free loop spaces. So actually, I am talking only of the small loops. So let V be a rank R complex vector bundle on M, and V tilde be V minus the trivial bundle of rank R. So then in the theory of elliptic genera, one considers Witten bundles. So there's not just one Witten bundle, but many of them, at least 4 I know. So let me just take a sample, θ2 and θ3. So these are elements in K theory of M, and with the power series Q to the 1/2 in terms of Q to the 1/2. And it's defined as such. It's a tensor product of, it's a kind of like exterior algebra of minus Q to the J minus 1/2 and exterior algebra of Q to the minus J minus 1/2 of V bar. Right, so V tilde and V tilde bar, and you have similar things for θQ, θ3. And Q is 2 pi, exponential 2 pi square root of minus 1 tau, where tau is in the upper half plane. And so Witten and some topologists in the 80s showed that these can be formally viewed as vector bundles over loop space, small loop space. So in some sense, it's like the tangent bundle, restricted to the tangent bundle loop space restricted to the constant loops, and you expand it. And physically, they appear in some heterotic string theory. So here, lambda t is this expansion of a vector bundle E is just the trivial bundle, t times E, t squared, lambda squared, E, and so on. And I just want to point out that, so here, in order to do any calculations, you assume that V is a direct sum of line bundles, and let 2 pi I x, sorry, this is square root of minus 1, and xi be the formal roots, Chern roots of V. So these are in terms of the line bundles. In terms of Jacobi theta functions, the Chern characters of the Witten bundles are these guys. So if you compute the Chern character, you get these theta functions of xi and tau. And these theta functions are certain number theoretic functions, which I'll just recall briefly in the next slide. And it lands in the even cohomology of M and as a power series in Q to the 1/2. So this is on the level of cohomology, but if you equip V with a connection, nabla V, and then the Chern characters can be represented by holomorphic functions on the upper half plane with values in even forms which have coefficient infinite series in Q to the 1/2. Now, of course, if you suppose that a certain condition which sort of resembles, which I told you the Pontryagin class comes up in this game. So if the half the Pontryagin class is 0, and this is also related to the fourth Chern class. So these, this is called the anomaly vanishing condition. Then the pth components, where p is even, of these theta bundles are modular forms of weight PO2 over certain subgroups of SL2Z, which I'll briefly explain. So I'll briefly point out later. So this is kind of motivation for what I'm going to define. So the next goal is to generalize this construction from finite dimensional vector bundles to infinite dimensional Hilbert gerbe modules. The reason is this is what's relevant for T-duality. Okay, so the gerbe modules are elements of twisted K-theory. These are representatives of twisted K-theory. I won't do full justice to it, but I'll just explain what these are. So let M be a closed smooth manifold of dimension 2R, H be a closed 3-form on M with integral periods. So this is, I'm just explaining that 3-form flux. So we have the B alpha and A alpha beta, and you have this triple, so H, B alpha, and A alpha beta. So this is the gerbe module, gerbe, I mean. And there's a geometric realization, so you have a line bundle on double overlaps, and the connection is D plus A alpha beta. Actually, maybe there's a square root of -1. So you get a geometric realization of gerbe with connection, and the curvature of this line bundle is just B beta minus B alpha. Okay, so because it's D A alpha beta, which is this. So now you want to get a module for this gerbe. So let me point out that if you take finite dimensional vector bundles and try and do this, it turns out there's a slight problem. That is, the gerbe has to be torsion. So therefore, you really have to deal with infinite dimensional vector bundles in order to get a module for a general gerbe. So let E be a collection, so E alpha be a collection of infinite dimensional, say, separable Hilbert spaces, Hilbert bundles, E alpha over U alpha. And okay, for twisted K theory, you need the structured group to be reduced to U tau, UT, so which are unitary operators on the model Hilbert space of the form identity plus trace class operator. Okay, so this is the model which we had in our old paper in 2002 with the 5 authors from Adelaide at that time. So, so tau is the Lie algebra of U tau, which is trace class operators on this model Hilbert space. And the key thing is on the overlaps, U alpha beta, so E alpha on overlaps doesn't match up, right? So, but there's a discrepancy, and it's given by the gerbe. So remember, the gerbe is this line bundles on overlaps. So if you take the line bundle L alpha beta and tensor with E beta, you get it's isomorphic. You're given this isomorphism with E alpha. So it doesn't patch up globally, but it's a module for this gerbe. So the gerbe acts on it, and it's compatible with the gerbe structure. So there's another relation which I haven't written out, but it's which says in words it's consistently defined on triple overlaps because of the gerbe property. So although this sounds mysterious, there's another way of doing it globally, but I don't want to explain it. There's too much things to set up. So this is easier. And E alpha is said to be a gerbe module for this gerbe L alpha beta. So you can also define a connection on this gerbe module. It's a collection of local connections of the form, and nabla E alpha is D plus AE alpha, where AE alpha is one form on U alpha tensor with trace class operators. And the curvature on overlaps satisfies this relation. So the curvature of E alpha and the curvature of E beta on the overlaps, it's related to the curvature of the line bundle times identity by this isomorphism phi alpha beta. Right, so yeah, it didn't. So this was the isomorphism phi alpha beta, and then using the relation that the curvature on the line 1 alpha beta is b alpha minus b beta, and rearranging, you get this identity. So the point is that if you take the trace here, these two terms are equal. So it's globally defined. And then by taking powers of this, you see that exponential minus b trace of exponential e to the minus the curvature of Fe minus the identity is globally defined. So this is essentially going to be the twisted Chern character, and because you subtract the identity because you can't take the trace of the identity, it's infinite dimensional. So you have this exponential starts off with the identity, so it's in order to cancel that. So we need to subtract. And supposing we have two gerbe module connections on the gerbe modules E and E prime respectively, the twisted Chern character, which is defined in this paper by the 5 authors here, is a map from twisted K-theory to even twisted cohomology, and it's defined as such. So here, because you're taking the difference, the identity terms cancel. So the model Hilbert space is the same for both, so that's why the identity is the same for both, and you cancel. So in some sense, the twisted Chern character on twisted K-theory is only defined not on individual gerbe modules, but on a pair of them.
What is G?
Yeah, that's a gerbe, sorry. You can replace that with H, you know. So, thanks. So the degree 0 term is 0. So let's look at the degree 2 term. It turns out to be the trace of the curvature of E minus trace of curvature of E prime, which is just an ordinary degree 2 class on Z. So the degree 2 component is just like a Chern class, okay? The degree 4 term, however, is really a gerbe version of the Pontryagin class. So if you calculate it, you get these terms, but you don't get rid of the b, you know, because there's a square. So it's an H4 of Z twisted by H. So now in this gerbe module case, the anomaly vanishing condition is that this term is 0, which is an ordinary Chern class, but there's a new one, which is a gerbe Chern class, also is 0. And in the case of the Witten module, the vanishing of the Pontryagin class gave the modularity of the that Chern character of the Witten genus. So here it'll similarly, this anomaly vanishing condition will give some, so we don't get modular forms, but you get Jacobi forms, and it gives that when you have this anomaly vanishing condition, what you get is a Jacobi form. Okay, so let's proceed with this. So we have this gerbe module E. So you can apply theta of E alpha locally, and it's the same formula. So it turns out, after a lot of checking, so you can see this in my paper, I didn't reproduce it here. It turns out that theta of E is actually globally defined gerbe module. But it's not a gerbe module for single gerbe, but it's a gerbe module for this tensor product of gerbes, so for all powers of M. So this is the reason why we wanted to include all powers of m, right? So all powers, mh for all h. So to compute the graded twisted Chern character, which is essentially the Chern character, but because you have all the different twists, we call it the graded Chern character, twisted Chern character. And again, we can't do it for just the Witten module of E. We have to take two such modules, gerbe modules, and look at the graded Chern character. What is it? So we just look at the terms Wmn of E prime. So these are gerbe modules for the gerbe Mh, Mb alpha, Ma alpha beta for each m and z. So you can therefore take the Chern character with respect to Mh of it, and then you sum over all m. So this is done in great detail in my paper. So you can't use just a homogeneous Chern character. There's a kind of graded Chern character. So this Q comes from the theta. There's a Q in the definition of theta. And y to the m just keeps track of the grading, keeps track of mh, so the m in the mh. So the main, one of the main results that we have is that under the twisted anomaly vanishing condition, which is those two things vanishing, so or as such, the graded twisted Chern character of this Witten gerbe module, or rather the quotient, is a Jacobi form. So it's the analog of what Witten did for just vector bundles. And these Jacobi forms, it turns out, is the right domain for T-duality on loops, on the small loop space. Okay, so that's the point. And here's an explicit example, which is the graded Chern character of the Witten genus, or Witten gerbe module. So this is just explaining the modularity. So you have SL2 with the usual action on upper half space. And then you have these various subgroups of finite index in SL2Z. So, and these Witten gerbe modules are modular with respect to these. Theta 2 is with respect to this, I think, and theta 3 is with respect to this. And you can write out generators, etc. And here's the theta function. I can't elucidate on that. It's some number theoretic function. It's an infinite product. And it satisfies various identities, which are very important in number theory. So let me just explain what Jacobi forms are. So let gamma be a subgroup of SL2Z of finite index, so like one of those which I wrote down in the previous slide. And let L be an integral lattice in Z inside a complex plane preserved by gamma, and denote by H the up half plane. And then a meromorphic Jacobi form of weight S and index L over this group, the semi-direct product, is a meromorphic function J of Z tau on complex plane cross upper half space, and it satisfies these identities. So J of Z C tau plus D, and this. It's just J of Z tau and some prefactor here, which is sort of like the modular thing, but it's different. It's a Jacobi form. So it's got these transformation laws, these two. So, but now we look at, these are just complex valued things, but we extend it to allow this J of Z tau to take values in differential forms on M. And we don't require it to be at the singular points to be poles, but just undefined. So let M be a manifold with a flux, and let A, K, well, let this denote the space of holomorphic functions on H with values inside differential forms on Z. Sorry, I meant M is Z, sorry, typo. And which are closed under D plus MH. And let Q denote e to the 2 pi square root of minus 1 tau, and tau is an H, and Y is this quantity. And on space-time, I seem to have stuffed up the M and the Z, sorry. So let's keep it as M. And further consider two-variable series. So omega of Z tau is these forms which are holomorphic on the upper half space and closed under this differential D plus MH times Ym. Okay, so this is just some formal variable Y which keeps track of the M. So it's represented by omega m of tau y to the m. So this is exactly analogous to how I repackaged T-duality, except that the forms now are not just forms, but they are holomorphic on the upper half plane, right? And have some Jacobi type property. So the expansion near y equals 0 is a Jacobi form of a suitable weight and index. So this is what is denoted by this funny symbol. So if you do the same level M Hori formula, et cetera, and we call it LT, so this is kind of loop T-duality. So it's exactly analogous to how I repackaged T-duality, right? So, and the upshot is that we get, so LT and LT hat are both isomorphisms of these modules. And we have to assume that the restriction of the y to the 0 component is 0 because you have to subtract off some infinity. And this composition is just the Euler operator both ways, LT hat, composite LT, LT, composite LT hat. And in fact, it maps this Jacobi forms to Jacobi forms with degree shifted. And you get a morphism of abelian groups. And this is the main result. But I just motivated it by repackaging ordinary T-duality. But it is more sophisticated because it includes the Q series, which appears in Witten's work. So since I have a little bit more time, so let me just tell you about an earlier version of T-duality, which is more lowbrow. It's earlier work with Fei Han in 2015. So the starting point was the following. So ordinary cohomology of Z is related to the equivariant cohomology of loop space, where the circle is the rotation of the loops. So, and this is an isomorphism under restriction. So you restrict and you put in the formal variables U inverse, and this is a power series in U inverse. So this is stated by Witten and proved by many mathematicians, but for instance, Jones and Petrak. So the only difference with the ordinary equivariant cohomology is because it's infinite dimensional, you need to take power series in U inverse. So it's not, if it's finite dimensional, you only have to take polynomials. So in this work with Fei Han, we were concerned with the analog of this result for twisted cohomology. So if you replace the cohomology here with twisted cohomology, the question is, what do you do over here? So naively, you might think it's some twisted equivalent cohomology of loop space, but it turns out that that's incorrect. So by the way, I should mention that the twisted cohomology was first studied by Röhm and Witten many years ago in '86. So here we define something called, there are too many words here, exotic equivalent cohomology. We could have used something else, but. So the key innovation is the construction of a canonical S1 equivalent superconnection on the holonomy line bundle of a gerbe with connection. And it also satisfies the localization, and the localization gives you the exact analog, and it reduces also to the case of that theorem of the equivalent cohomology of loop space. It's just the cohomology of the space itself, suitably localized. And so, sorry, there's some redundancy here, so let me skip this. So there's some open cover of of Z, which for which you have the H alpha, H restricted to U alpha is dB alpha, and B alpha minus B beta is dA alpha. So for this to work, you only need that H2 and H3 are 0 for all overlaps. Okay, so we don't want any condition on H1, otherwise you can't get a hold of large loops. So, so then the loop space is covered by loops of these open sets, right? So there are many constructions, by the way, to get this, but let me just take this one. So in a gerbe, as I said, these line bundles on the overlaps, and you have a trivialization of the triple tensor product of these line bundles. So this is a geometric version of what I told you before, and this phi is the Dixmay-Doudet invariant of the gerbe. So it's actually an H3 of Z integral cohomology. And the trivial gerbe is always of this form, L alpha tensor L beta, where L alpha is a line bundle on just the open set. So any collection of line bundles on open sets gives you a trivial gerbe as such. So this picture, well, I won't go through the examples of this. So here's, so since we are given this these line bundles, and the connection, so D plus A alpha beta, and the curvature is B beta minus B alpha. So then, this is a gerbe with connection, and this gerbe, there is a holonomy line bundle. I just want to sort of give you the construction of this. So it's interesting, it's very easy. So this is a line bundle on loop space. This is the holonomy of this gerbe. So it has invariant Brzezinski local section sigma alpha with respect to this open sets. And the transition functions are exponential square root of -1, the transgression of A alpha beta. So this is the transition functions of the line bundle. And the transgression map, just recall that all it does is pulls back a form on loop space of, and under the evaluation map, and integrates over the circle. So this transgression of this one form is just a function. And so this is the, so here it completely defines the holonomy line bundle. So the curvature of this holonomy line bundle, it's a line bundle with connection, so the connection is D minus square root of -1 transgression of B alpha. And the curvature is just a transgression of H times a constant. And so just note that this line bundle is never really flat, because H is not 0, so the transgression of H is not 0. And so we consider the space of differential forms on loop space with values in this line, on this holonomy line bundle, right? And then, so there is a way to, so I just have 5 more minutes, I guess. Is it? Sorry. Okay, thanks. So if you take a differential form on Z, so Z can be thought of, the manifold can be thought of as a constant loops inside loop space. So you take a form, an I form, and there's a construction of an I form on loop space by just extending this form as such. So you take little s in 0, 1, so omega hat of s. So at x1 to xi is omega of x1 and xi are vector fields on loop space defined near gamma. Gamma is a loop, and you're evaluating at gamma of s. So one checks that D commutes with this hat operation. And then to get rid of the s, you just integrate from 0 to 1. And you still get an I form on loop space. So this form that you get is invariant, is under the rotation. So the lead derivative of the rotation vector field of omega bar is 0, and d omega bar is d omega bar. So it commutes with the bar, d. And also the transgression map can be nicely written as a contraction with respect to the rotation vector field of omega bar. So this has been used by people like Bismuth, so for his proof of the index theorem via loop spaces. So this construction, it's very useful. So let H be the 3 form on the manifold, and extend it to loop space by the bar operation. Okay, so it's, as we saw, it's invariant. And now I'm going to define an operator dH bar, which is the connection on the holonomy line bundle, plus H bar minus contraction by the rotation vector field. So the point is that the square of this operator is 0 on the invariant forms with values in the holonomy line bundle. And the calculation, I don't want to go through it in detail, but it's essentially the Witten conjugation trick, like he did for Morse theory by conjugating the de Rham operator. But here, by the Morse function, but here we conjugate by the 2 form B alpha bar. Okay, and you get the square is 0 on the invariant forms. So it's the lead derivative, which is 0 on the invariant forms.
Sorry, what was K again?
The rotation vector field, rotating the loops. So this is on loop space. So the point is that this object is a flat circular equivariant superconnection in the sense equivalent. And this is a Z2 graded complex. And the cohomology of this complex is the equivariant cohomology, which I was stating. And our main theorem is the localization theorem, which says that this localizes by restriction to the twisted cohomology and is an isomorphism. Yeah, I mean, I think I'll end here because I've gone over time. Thank you for your time. Yeah.
I think we have time for a quick question or two.
Yeah.
So for the gerbe Pontryagin class, it has B in it. Is B closed or not? I'm thinking of Chen-Wei theory.
No, DB is H.
Yes, so H is DB, so B is not closed.
No, it's only local.
Local.
This notation was just to simplify, but it's really B alpha
Right. You're working on patches, as in
Yeah.
twisted churn characters.
That's
E to the
right.
B.
Exactly.
Yeah. Right. Okay.
And that, the component of degree 4 is global,
Yes.
but each term is local.
Thanks.
Sorry, I don't know where it is. But it's probably- yeah, here. So this is just a fake notation. It's like this E alpha. So B alpha, F E alpha.
Sure. It's
Yeah,
local.
yeah,
Yeah.
yeah.
Thanks.
Okay, thanks.
So
Yeah.
in your T-duality formulation, is there a concept of winding number, like momentum winding number?
Yeah, I mean, not in this version, but we are refining it further. So in earlier work on T-duality, not on loop space, but so Faye and I sort of extended. So yeah, I can just point that out. Thanks for bringing it up. So
Because I saw a two-variable lipid genus somewhere.
yeah,
So usually that is those two recipees are like the winding number, the momentum number.
uh,
So that's why that's the reason for my question.
possibly, yeah. But here, right, I mean, in the original T-duality, which I did with Jara and Peter, there was a slight problem in the sense that it was only defined on invariant forms. So this was slightly problematic when it came to winding and momentum because the winding is along the circle and you can't see it here. So Faye and I sort of studied this problem because I guess Maxime pointed it out, and we extended this T-duality to beyond invariant forms. So you can extend it to all forms on this side. But the interesting thing, we wrote another paper in 2018, that on the T-dual side, you don't get all forms. You get sort of exotic differential forms. So, and that takes into account, you can formulate winding and momentum, and it takes, T-duality exchanges both under that. So over here, I didn't take into account, when I did the small loops extension, I didn't take into account this extension. So we still stick to invariant forms, but we are now looking at the case of removing the invariance, and then we can properly formulate winding and momentum in that case. So it's a bit harder to do that, but nevertheless, it's been done in the ordinary case.
Okay. Iris, do you want a quick? Well,
Yeah.
Maybe I'll do another coffee.
all right. Let's thank my guests
you.
again, and maybe come back at 15:15.
Thanks.